Hello everybody. In this video we're going to start with one example where we are going to apply the general diffusion equation or the continuity equation with the flux equation, and we were going to apply the procedure that we discussed in the previous video, and I believe this will make the process clearer and the steps more understandable than just the theoretical steps that we mentioned in the last video. So in this example that we have here, it's discussing the process of fabrication of some microelectronic devices that are silicon based, and it's talking about a silicon wafer, which is something like what we see here. It's a disc that is made of pure silicon, and that's why it's called silicon wafer, and they are so they are used in many applications, and that's why the surface might be like changed a little bit by doing some deposition of some material, so that the silicon wafer is suitable for the application that it is intended for. So in this case, we have a reaction here that we see on in here, which is the reaction of silicon hydride on the surface of silicon to produce silicon and hydrogen gas, and this silicon is the solid that's depositing on the surface of the silicon wafer. So this is the reaction that takes place. And we have here this process called chemical vapor deposition, as we see here. And this is what we see here, that there is this chamber, which is the reactor. We have the silicon hydride vapor, or what we call the silane vapor, and the hydrogen gas, and they enter from the left-hand side. And they keep going until they come out from the other side. And while they are going from left to right, some of the silicon hydride diffuses through this diffuser. And this is the area of interest, or the region of interest to us, which is the region where molecular diffusion takes place. So here the silicon hydride diffuses from this dotted line, this diffuser, into the surface of the silicon wafer. The reaction takes place, and then the hydrogen gas diffuses back to the diffuser and leaves with the gas mixture. And the diffuser is at height of Z equals 0, and the film is at, or the silicon wafer is at Z equals delta. And here we are gonna read read the text or the problem statement, and I will stop at some sentences because they are useful, and they will be the basis of some of the steps that we will do in the solution. So the first sentence here says that the surface reaction is carried out at very low pressure and high temperature, which is okay. It's not gonna help us in the mass transfer calculations. And now the next is that the gas phase over the silicon film is not mixed, and by this we mean that there is no device for changing the airflow, or a pump or a compressor or something like this. So there is nothing like this, nothing to do the mixing, which means that the diffusion or mass transfer is mainly or totally by molecular diffusion. The second piece of information here is that the surface reaction is very rapid, and this means that this is something that we talked about in the boundary conditions before, and we said that a very fast reaction or a very rapid reaction means that the concentration of the reactant in the surface is 0. And here it says that the molecular diffusion of silicon hydride vapor to the surface often controls the rate of silicon film formation. So this sentence means that the rate of silicon formation is not dependent on the speed of the reaction, because the reaction is very, very quick. So the step that controls the formation of silicon is not the reaction, it is the diffusion of silicon hydride, and this is what this sentence is about. There is another sentence here that it says that the mixture of silane and hydrogen flow into the reactor, and then it says the feed gas provides silane in high excess relative to the amount consumed. So the amount of silane that's available here is much more than what we need to, or what diffuses here in this area. which means that the concentration of silane here is almost constant because it's not going to be affected by the small amount that is diffusing through the diffuser. And the last sentence here, it says the diffuser provides a stagnant gas space over the growing silicon film. It means that the region over here is stagnant, which is another way of saying that the gas phase over silicon film is not mixed. So it's again confirming that it is just molecular diffusion mass transfer. The requirement in this problem is to develop a differential model for the process, including statement and assumptions and statement of assumptions and boundary conditions. So in this chapter, it's not concerned with the solution of the problems. So it's mainly focusing on the developing the equation and getting the final form of the equation. But because this problem is simple, we can go further and get some outputs out of it. So first, let's talk about the assumptions. So there are many assumptions that we already know here in this problem. So first, we know that the reaction only takes place on the silicon film. So in the diffusing area, there is no reaction. So R equals 0. There is no gas mixing, which means that it's all molecular diffusion. We said that. The feed provides silane and high excess, which means that the concentration of silane in here or at the diffuser is constant. This is a very important point, that the flux is one-dimensional, and the reason we claim that is that our understanding of the problem would be the main source of this piece of information. We don't have any evidence that there is a gradient in y or x direction. It's only in z direction. The concentration all over this area is or this length is the same, and it's all going down, and then the hydrogen is coming up. So we can claim that the concentration is only dependent on z. It's not changing with y or with x. And again, this is one thing that I mentioned earlier, and I confirm it again, that the understanding of the problem is the most important step before even starting to solve the problem, because if you do not understand the problem well, you cannot put the equations that really reflect what is going on in the real system. So this, and especially for this point, because this is the very first point that, or very first step that we do after writing the continuity equation, is that we cancel out the zero terms, and these zero terms are defined based on an assumption like this. So if you say that it is one-dimensional or flux is one-dimensional in z direction, then you will cancel the y and x components of the equation. And if it's not right, then you have the first step not right, and everything that's gonna be dependent on it is not gonna be right either. So that's why we have to make sure that this assumption is put properly or put correctly. And then the next is that the film thickness is very small. So we say that silicon is deposited on the surface of the silicon wafer. So if you claim that, and this is a very, very valid assumption, is that the film that is depositing on the surface of the silicon wafer is very, very thin compared to this distance. And this makes a lot of sense, because this is a film that is on a molecular level, so it's very, very small compared to delta. So this delta is always constant, so it's not changing with time. And then mass transfer is steady state, and this is an important assumption as well, because we have here a continuous flow of silicon hydride. It's totally consumed here, and then hydrogen is diffusing the other way. So we have a continuous flow in and out, which means that we are operating at steady state. So these are the assumptions, and now let's see how we can deal with this problem using the equations. So we will start with the continuity equation. Based on our assumptions, we said it's one-dimensional, it's only on z directions. Then we will cancel x component and y component. We said that there is no reaction, so r is 0, it's steady state, so partial c partial t equals 0. So we will end up with dna z by dz equals 0. And now we put it as d because it's now an ordinary differential equation, because we don't have, or we have only one independent variable. And from this we can get an output that NAZ is constant. I'd like to go back and check the block diagram. Now we have put the differential equation, we applied our assumptions, and we got the simplified differential equation of mass transfer. So this is where we are right now. We have the simplified equation, and it's in the terms of NA. And as we said, we have two routes, either to go this way or to go this way. But in our case, the equation is saying that NA is constant, so we don't have any other output that we can get from this equation. We have already integrated the equation, and its output is that NA equals constant. So this is all what we can get. So we will go through this route now. We will go through fixed equation and get the integral form of fixed equation, and then get the concentration profile. So what we need according to the problem statement is just the differential equation. And this is what we will see now when we go back to the problem. We need to write the form of the flux equation, which is the general form, and then we have we can use this equation directly, but we have here something here that we cannot use directly. We have here NAZ and NBZ, and we cannot use these equations or we have to get rid of one of them, so that we have only one variable, which is in A and Z direction. And this is something we can get, and by the way, A is the silane and B is the hydrogen. And what we can do is to use the reaction stoichiometry, which is this. So each mole of A produces 2 moles of B, and it diffuses the other way. And this is something we mentioned earlier about the reactions. So this is an output that we can get, that NBZ equals -2 NAZ. So if we substitute with this equation here, we can get the equation in the form of or in terms of NA. So we got rid of NBZ now, and it's all in terms of NA. We can rearrange the equation so that we have NAZ as a function of the rest of the parameters. So we will get NAZ as a common factor, and then we divide by 1 plus YA, and this is NAZ in the differential form. So let's go back. This is the fixed equation in the differential form. This is what we did. We got the information from here, we put it here to get, or we haven't got this information, but what we have is the fixed equation in the differential form. We need to use this equation that we got from here with this to get the next part of the block diagram, or the next step in the procedure. So we need to use this equation. So it's now a differential equation. We can use it by integrating it, and by integrating the equation we can use the information of NA is constant by getting N out of the integration, because it's constant, it's not going to be part of the integration. And now we have DZ as the left hand side, and the right hand side -C DAB, and DYA divided by 1 plus YA. We can assume that C and DAB are constants. We are operating at constant temperature and pressure, so this is kind of a valid assumption. So we can do the integration of 1 plus YA equals ln 1 plus YA from YA naught to YAS, and then this is how the equation is looks like. And then we have the form of NAZ as a function of the parameters that we have. So NAZ equals C multiplied by DAB divided by delta multiplied by ln 1 plus YA naught plus divided 1 plus YAS. And we know that the concentration here is 0, which is YAS, which is the surface. So this is 0. I'll go back here and then see. So we got the integral form of NA here as a function of the rest of the parameters. But here you will see something that we have already done the analytical integrations, but we haven't used the boundary condition, or it seems that we haven't seen the boundary conditions in the solution that we have. So we said that the boundary conditions can be used in case I have an integration and then I have an integration constant, and I use the boundary conditions to get the integration constant. And this is what we said earlier. But actually the boundary conditions can be used this way, to have a constant and then use the boundary conditions, substitute in the equation, get the value of this constant, and then re-put it back in the equation, or to put it as boundary conditions like what we did here. So we have here these are the boundary conditions from 0 to delta. which is the boundaries, and we have it from YA node, which is the concentration here, and YAS, which is YA on the surface of the silicon wafer. We put it as a general form. We know that this is 0, but we just put it in a general form so that it's valid for any case. So this is how we use the boundary conditions, and this is the form of NAZ. So this is the flux or the output that we wanted from the problem statement to get the flux with the boundary conditions and the assumption. So we are now done. But in this problem, I got a question about the concentration profile, if we want to get the concentration profile. And this is something we can see here in the block diagram, that you can get the concentration profile, which is the concentration as a function of distance. So at any z, I can get the value of the concentration. And this is doable in this problem. It's a simple problem, just one-dimensional, steady state, no reaction. So it's a very simple case. And to get the concentration profile, you might feel that this is kind of tricky, but it's actually very simple. We just need to look at this equation. So what we did in this equation is that we put boundary conditions that are constants. We have constant 0, we have delta, we have YAS, YA naught. They're all values. They are not variables. They are values, that the constant values. So NA is going to be, I don't know if it's clear, but NA from this equation is constant. It's just NA, C is constant, DAB is constant, delta is constant, YA node, YAS, they're all constant. So the equation is constant. It's gonna give a value of the flux. But if I want to get the concentration or the mole fraction at any distance, then I have to do something with the boundary conditions. So I'm gonna start with 0 and YA node. And this is where the diffusion starts, and I'm going down, but I'm not gonna go to delta. I'm gonna go to any value of z. So this is the main difference. I'm going to make the boundaries from 0 to z, and from YA node to any y. So this corresponds to this. The y corresponds to z, and by this way we can get the general form of the concentration profile, and then we can get the concentration at any point. So this is what we are doing here. We do the integration the same way we did last time. The main difference, or the only difference, is that this is z and this is YA. This is YA instead of YAS before. And I have now the relation between YA and z, but I have NAZ here, which is a function of other parameters. So I can re-simplify or simplify the equation more by getting the formula of NAZ and plugging it into here. So the equation would be like this, and we will cancel some terms here that are on the right and left hand side, CDAB, CDAB, and with some mathematical manipulations we can have the equation written in this form or in this form. So they're both the same, and this will give us a chance to get a more closer or look at the concentration profile. This is what we see here, that the from this equation you can have the z over delta, which represents the distance, and this is what I have on x-axis here, and this is a very good way of representing the variables, to put them in dimensionless forms. One reason, because it's not gonna have dimensions, so you don't have the issues with writing the units and all these things. The other is that it has a value which is a limited maximum and minimum values. So no matter how big or how small the delta is, z over delta will start with 0 when the distance is 0, and with 1 when z equals delta. So it's bounded between 0 and 1, and this is what we can see here, that this is from 0 to 1. Might not be clear here, but I think maybe you can see it now, but this is from 0 to 1. And here you can see YA at different initial values of YA. So you see here YA node is part of the equation. So if YA node is, if you put YA node with 0.9, this is the very first point here. If you put z equals 0, then this is all power 0, so this bracket is going to be 1, and I'll have 1 plus ya node minus 1, which is ya node. So now at z equals 0, y equals ya node, which is logical, which makes, and this is one thing that you can do to check the equation and make sure that it's valid and it's logical, is to put an extreme case and see what happens. So if I put it as 0, then this is going to be or I mean with 0, this is going to be 1, and then I'm ending up with ya node. And if I put it as z equals delta, then the equation will end up with yas. So it's again, it's confirming that everything is okay, that I'm writing the equation which is valid for at least two boundaries, or the two cases that I'm sure of their outputs. And this is how the profile will look like, and at different initial values of or values of ya node. And for all the cases, the last point is at 0, y equals 0, at z over delta equals 1. So this is the first example. Next video, inshallah, we will see another example that's kind of more advanced than this one. So I'll see you then, inshallah. Goodbye.